options here. And so we know that x is equal to 0.9475 and 1.305. And since we are supposed to give our answer to one decimal place, we know that answer for x would be 0.9 and 1.3, hence solving this question. So in question 9, we've been given a table showing the annual global production of plastics measured in millions of tons per year for 6 selected years. And it is thought that this relationship can be modeled by the equation P is equal to A times 10 to the power KT, where T is the number of years after 1980 and A and K are constants. Now in part A, we've been asked to show algebraically that the graph of log base 10 of P against T should be linear. So essentially, in order to show something as linear, we need to bring it within the form of y equals mx plus c, where m is the coefficient of x and c is just a constant. So we can go ahead and just attack this question directly. Well, if we have P is equal to A times 10 to the power KT, well, we know that we need to get the graph of log base 10 of P. So I'm just going to go ahead and add log base 10 to both sides. So here I get log base 10 of P is equal to the log of base 10 of A times 10 KT. Now, we know from our logarithmic rules that whenever we have a multiplication within a logarithm, we can split that logarithm by addition. So essentially, this equation will expand into log base 10 of P is equal to log base 10 of A plus log base 10 of 10 to the power KT. Now, we know that whenever we have the base equal to the value in the logarithm, that logarithm just equals the power. So we can essentially simplify log 10 base 10 into the following. So we get log base 10 of P is equal to log 10 of A plus KT. And then, of course, you can go ahead and rearrange this even further to get log base 10 of P is equal to KT plus log base 10 of A, which is indeed in the form of y equals mx plus c, where y in our case is log base 10p, m is k, t is our x, and log base 10a is our c, hence solving this question. So in the first part of question 9b, we've been asked to complete the table below, where we've been given the values of t and the respective values of log base 10 of p. Now, to solve this question, we have to go ahead and use the table that we've been given at the start of the equation, where we have been given the values of P as well as the years that they're associated to. Now, remember, T is the number of years after 1980, which means that when T is equal to 0, this year is 1980. So I can just go ahead and, for reference, write that year down here. So if I make a row here on the table, then I know this is 1980, I know that this is 1985, this is 1990, this is 1995, this is 2000, and this is 2005. And so we can go ahead and just write down the values of P for these individual years as well. And if you want, you can check for the given values. So the given values for P here are 75, 94, 120, 156, 206, and 260. Now, if you want to go ahead and make sure that the way we're working out this question is correct, you can go ahead and check that log base 10 of 75 is actually indeed a 1.88, and that holds true for each of the given values here. So we can go ahead and calculate with assurance the values that we need to calculate in these two hidden blocks. So if I go ahead and put in our calculator log base 10 of 156, I get the answer 2.19. And if I go ahead and do the same thing for log base 10 of 260 for the year 2005, I get the answer 2.41, hence solving this question. So for the next part of this question, we've been asked to plot graphically the values for log base 10p against t, and also draw a line of best fit for the data. So I'm going to go ahead and plot the data now. So for t is equal to 0, we have a value of log base 10p as 1.88. So 1.88 would roughly be around here. So this is 1.1, this is 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, and 1.9 here. So 1.88 would roughly be around here. Roughly be around that point there. Next, for t is equal to 5, log base 10 is equal to 1.97. So that's going to be really close to the 2 here. For t is equal to 10, log base 10 of p is equal to 2.08. So that'll be really close to 2.1 here, roughly here. And then when t is equal to 15, log base 10p is equal to 2.19. So this is just going to be, again, another whole point roughly above the previous point. So close to where 2.2 would be. So 2.2 is around here. So 2.19, we're really close by, roughly there. And the next point for t is equal to 20, log base 10p is equal to 2.31. So again, if this is 2.2, this is 2.3, 2.31 will be slightly higher than 2.3. So roughly around there. And then finally for t is equal to 25, log base 10p is equal to 2.41. So that again would be a whole sort of point ahead. So this is 2.3, this is 2.4, 2.41 would be roughly here. So we have our points plotted. If I go ahead and draw a line of best fit, I'll do this in a different color so it's easier for you guys to see. We can draw it from t is equal to 0 all the way to t is equal to 25. A line of best fit like that, where it roughly touches all the points, should be more than adequate. And that thus solves the second B part of question 9. So for the first part of question 9c, we have been asked to hence show that k is approximately equal to 0.02. Now, if you remember, our equation was essentially that log 10 of p is equal to kt plus log a. And essentially k here is our gradient of the linear line that we plotted in the previous part. So I'm just going to go ahead and calculate the gradient using the gradient formula by taking 2 points on the line. Ideally, I like to take the first and last point as they are most likely going to be on the line of best fit. So our first point here is 0,1.88 from our graph, and our second point is 25,2.41. And we know that our gradient, or m, is equal to the change in y upon the change in x, which in our case is the change in log base 10p upon the change in t. And so if I go ahead and calculate that, that essentially looks like 2.41 minus 1.88 upon 25 minus 0, and that is equal to 0.212. Hence showing that this is approximately equal to 0.02 when we round down. Hence showing that k is approximately equal to 0.02. I should probably write k here instead of m. I'm used to using the generic sort of notation for gradient, but essentially here is this question solved. So finally, in the second part of question 9c, we've been asked to find the value of a. And again, all we have to do here is refer back to our equation where we have log base 10p is equal to kt plus log a. So log a here would be our y-intercept, and we already have the coordinates of our y-intercept from the previous part, which is 1.88. So if we know that log base 10 of a is equal to 1.88, we know that a is equal to 10 to the power 1.88, which is roughly equal to 75. Hence solving this question. So in question 9d, we have been asked to use the model with k is equal to 0.02 to predict the number of tons of annual global production of plastics in 2030. So here, essentially, we just have to input the value of K into our equation. So we know that our equation is equal to log base 10 of P is equal to KT, which is 0.02T plus log base 10 of A, which we know that A is equal to 75. So this should just be log base 10 of 75. Now, we need to find the number of tons produced in 2030. And we know that 2030 is 50 years after 1980. So essentially our T would be equal to 50. So T is equal to 50. So log base 10 of P would be equal to 0.02 times 50 plus log base 10 of 75. Now, if you put this into your calculator, you should get the value of log base 10 of P is equal to 2.88 roughly. And that means that if we rearrange, we know that P is equal to 10 to the power of 2.88. And we know that this is equal to 750, which is our answer, but it's not our final answer, because if you read carefully in the question, P is measured in millions of tons. So this would be 750 million tons, hence solving this question. So in question 9E, we've been asked to use the model with K is equal to 0.02 to predict the year in which P first exceeds 8,000. So if I go ahead and write our equation again in the same way, we know that log of base 10 of P is equal to 0.02T plus log of base 10 of 75. So we know here that we need to predict the point at which P exceeds 8,000. So we can go ahead and substitute P is equal to 8,000 into this equation. And we get log base 10 of 8,000 is equal to 0.02T plus log of base 10 of 75. And then I can rearrange this equation and I get log of base 10 of 8,000 minus log of base 10 of 75 is equal to 0.02T. And then divide the whole thing through by 0.02 to yield my value of T. So T would be equal to log of base 10 of 8,000 minus log of base 10 of 75, with the whole thing being divided by 0.02. And this yields T to be equal to around 102 years, if I round to the nearest number. And since T is equal to 102 years, we know that 102 years after 1980 would be equal to 2082. So the year 2082 is when P would exceed 8,000 million tons. For question 9F, we've been asked to give a reason why it may be inappropriate to use this model to make predictions about future annual global production of plastics. Now, if you remember from our graphical representation of this model, there was an increasing trend in the production of plastics. Now, in real life, this may not be the case. Why? Because consumer demands change every year. People decide that they want a different thing one year and then a different thing the other, especially in the case of plastics. For those of you who have been sort of paying attention to the sustainability initiatives of recent years, many companies are vouching for using less plastics. So in likelihood, the sort of demand for plastic production may decrease in the future. And so any sort of reason around that would be more than sufficient for this question. So I like to go with the fact that plastic production may decrease in later years. A very simple answer like that may be sufficient. If you want to be on the safer side, give a reason. For example, due to changing demands, and that should be more than enough to yield that 1 mark.